Okay, welcome to Warm Up 9.1. This is some Chapter 8 material, actually, because I haven't, I always do these warm-ups before I actually start the section. So these are some commonly missed problems in Chapter 8. So on the first one, are these two triangles similar? If so, I'm going to explain and write a similarity statement. And when I say explain, I'm just going to say what theorem I'm using. Or postulate or whatever. Okay, so in this case, I've only really got three options for finding triangles similar. I could do AA if I have two sets of angles that are congruent. I could do SSS if I got three sets of sides in proportion. I could do SAS if I've got an included angle. So I don't have any sides here to deal with. I don't have any way to find any of the side measures. So I'm going to be looking for AA. And I can see right off the bat I've got one pair of congruent angles. So I need to find one more. Hey, 130 is not equal to 20 degrees, so that's not a match. But I've got missing angles in both triangles. So what I'm going to have to do is use the triangle sum theorem, which just says the three interior angles are going to always add up to 180. So the measure of angle J plus 30 plus 20 degrees is all going to equal 180 degrees. Okay, so then I'll solve for J here. I'm going to combine my like terms. Okay, and then I'll subtract 50. And the measure of angle J then is going to be 130 degrees. Okay. So, hey, now I do have a second pair. Okay, so when you're missing angles in triangles like this, find the missing angles because that might lead to a match. You could have also found angle B down here and it would have turned out that it's 20 degrees. So these would also be congruent. So my answer here is yes. These triangles are similar. Okay, my explanation, I used AA. So here's my explanation. This is the AA triangle similarity postulate. It's important to put that similarity symbol because this is not a congruency theorem, it's a similarity theorem. Okay. Okay, and then a similarity statement. So you can name the first triangle however you want. I'll go alphabetical. I'll go JMN. Triangle JMN is going to be similar to the other triangle, but now I have to make sure I name my second triangle in the same order. So angle J is going to correspond to angle C. So since I put J in the first slot here, that means I need C in the first slot here, right? And I have to continue in that fashion. So M is going to match up with A. So A goes there, and then N matches up with B. So name the first triangle however you want, but then the second triangle, make sure you get the congruent angles in the same positions. Okay? All right, next up. We're going to solve for x. So I've got these parallel lines, so it's tempting to think about the side splitter theorem, which would say this is to that as this segment is to that segment, but I don't have enough information there. I don't have the measures of these segments or that one. So I'm going to have to do something else. I'm actually not going to use the 11 at all. The 11 is kind of a distractor. So I'm looking for corresponding pieces here. I have the 3 and the 8. Those are the bottom of both triangles. Okay. So then I want to use the right side of these triangles. Well, the right side of the small triangle is x, and the right side of the big triangle is 12. So those are going to be matching pieces. So I don't have to come up with a name for this segment down here because that's not the side to a triangle, right? So I'm comparing the side of the little triangle to the whole right side of the big triangle. That would be the x and the 12. So 3 is going to be to 8 as x is to 12. I can't reduce there, so I'll go straight to cross multiplying. And that means 8x is going to equal 36. 3 times 12 is 36. And divide by 8. Okay, so I've got 36 over 8. Let's go ahead and reduce that. 4 goes into 36 and 8. That would be 9 over 2, or 4.5, or 4.5. Okay, and there's x. All right, and the last one, we've got these similar figures. So Very common mistake that gets made here. So I'll do this the wrong way up here. This is the common mistake. People will say, oh, x is to 8 as 49 is to 100. That is incorrect, because what that means is that we're using 49 over 100 is going to be the area ratio. These are both areas, but these are not areas. These are sides. So I'd be using the area ratio to compare the sides, and I don't want to do that. Okay? So I've got to do a little bit more work here, a little side problem. So the area ratio, let's start by finding that, since I have both areas. So my area ratio is going to be 49 over 100. Okay? And just a little tip, you'd want to usually reduce these if you can. This one you can't reduce, so I'm good there. Okay? But I don't want to use the area ratio. I want the side ratio so that I can compare and find my unknown side. So my side ratio, I can get that from the area ratio. Okay? So if you know the side ratio, you square it to get the area ratio. But if you're going the opposite direction, you're going to take the square root. So my side ratio is going to be the square root of 49 over the square root of 100. And lucky for me, those are both nice perfect squares. So square root of 49 is 7. Square root of 100 is 10. So my side ratio is 7 to 10. So when I write my proportion, I want to say that 7 is to 10 as my small side is to my big side. So x is to 8. And then I can cross multiply and solve. So 10x is going to equal 56. 7 times 8 is 56, right? And then I divide by 10. And yeah, you could do a fraction here. I'm just going to think, hey, 56 divided by 10 would be 5.6. But you could do the fraction version of that as well, as long as it's reduced. Okay, and that is the end of the warm-up, and I'll see you next time.